In this module, we're going to talk about two bonding theories, valence bond theory and hybridization theory. Both of these are attempts to explain what atoms do when they form bonds to other atoms to make molecules. So first, valence bond theory. Basically just says that when a bond forms, it's an atomic orbital from one atom overlapping with an atomic orbital from another atom, resulting in a lower energy for those atoms. So if we look at hydrogen, the hydrogen molecule, and imagine we're going from the right in this graph to the left. If we start with two hydrogen atoms far apart from each other, the overall potential energy of those atoms is something like this, a little bit below zero. As we start bringing these two atoms closer together, the 1s orbital on this atom and the 1s orbital on this atom start to overlap, which means that allows some of the electrons from each of the atoms to be right between the two nuclei, which lowers the energy. You get negative charges close to positive charges, you lower the energy. And the energy starts going down. And the closer to those two atoms get to each other, the lower the energy gets. But it doesn't go forever. If they get too close to each other, the nuclei start repelling each other. The protons in the nuclei start pushing each other apart, and the energy starts going up. So there's this one distance that's the minimum energy for these two atoms to be apart from each other. And that's what we call the average bond length for, in this case, for hydrogen, or for whatever the atoms are. And valence bond theory basically says that you have the valence electrons in an atom, in whatever orbitals they're in, those orbitals overlap with valence orbitals in another atom to make a bond. Like, for example, in hydrogen sulfide. We know that sulfur, its electron configuration in the ground state is neon 3s2, 3p4. And the 4 electrons, if we write them out where they're at, there's 2 of them in one orbital, 1 in each of the other orbitals. And hydrogen, of course, is just 1s1. So in hydrogen sulfide, valence bond theory is successful in predicting what it does. We have 2 orbitals that have 1 electron. That's what valence theory says, is that you're going to have 1 electron from this atom, sulfur, 1 electron from the hydrogen atom, overlapping. Maybe I should write that. Hydrogen is 1s1, which is just 1 electron. And so one of these electrons overlaps with one of these electrons, with this electron in this hydrogen atom, and you make a bond. The other thing about p orbitals that's relevant here is that p orbitals are on the same atom are always 90 degrees to each other. We have 3 p orbitals. We call them px, py, and pz, and they're all 90 degrees to each other. And that predicts that in hydrogen sulfide, because we have 2 bonds between the sulfur and hydrogens, each is in a different p orbital. These p orbitals are 90 degrees to each other. The bonds should be 90 degrees to each other, and in fact they are. And see these 2 electrons here? They're not forming any bonds. They're a lone pair of electrons on the sulfur. So that's somewhat successful. That's valence bond theory. But when we get to some other molecules, it doesn't quite work. For example, if we look at carbon, we know that carbon's electron configuration in the ground state is helium 2s2, 2p2. So the 2s subshell is full. The 2p subshell has 2 unpaired electrons in it. And so valence bond theory predicts that carbon would form 2 bonds to hydrogen, just like sulfur did, and those bonds would be 90 degrees to each other, something like this. We do not see this molecule in reality, not for very long anyway. It's pretty unstable. What we do know about carbon is that when it reacts with hydrogen, it makes methane, CH4. And what we know about methane is that all 4 hydrogens are equivalent. The bond angles are all the same in this molecule. The bond lengths are all the same. And that bond angle is 109.47 degrees or so. Tetrahedral bond angle. It's tetrahedral geometry. And so there's no way that valence bond theory is going to match up with experiment, the 109.47 degrees in the tetrahedral geometry, because those p orbitals are 90 degrees to each other. So we have to come up with something else. What they came up with next was called hybridization theory. And what we do with hybridization theory, quite simply, is we hybridize or mix together the valence orbitals in an atom. So carbon is helium 2s2 2p2, so we take the 2s in carbon and the 3 2p orbitals, throw them in a barrel, mix them all up, and come out with 4 identical orbitals that are a combination of the s and the p. And an sp3 hybrid orbital looks something like this. We say it has 25% s character and 75% p character because it's 1/4 s and 3/4 p. And here's the good thing. Those equivalent sp3 hybrid orbitals are all 109.47 degrees from each other, and they form a tetrahedron. It's kind of hard to see here, but this is one orbital. This would be kind of pointing in on the carbon nucleus. This would be out, available for overlap. In terms of the energies, this is a neutral carbon atom. It's helium 2s2 2p2. When we hybridize the orbitals, what we get, the hybrid orbitals, first of all, however many orbitals we mix together, that's how many orbitals we get out. So here we're going to mix 1 2s and 3 2p's, and we get 4 sp3s. Also, the energies of the hybrid orbitals are between the 2s, or the s, and the p. So this is energy on this axis here. 2s is lower, 2p's higher, sp3 is right in the middle there somewhere. We take these 4 electrons, we put them into these 4 orbitals. Now we have 4 orbitals that are 109.47 degrees from each other, form a tetrahedron. Each has 1 unpaired electron in it. So now each of these can overlap with a hydrogen 1s orbital, make a bond, and get methane, CH4. Now, if we have a trigonal planar electron group geometry, notice I'm saying electron group geometry here, okay? That's the important thing. You'll see in the last bit here of this module that what this really comes down to is electron group geometry. That's how you predict hybridization. And what I'm doing here, by the way, is I'm explaining a little bit of where this comes from. What you have to do as a practical matter is basically look at a Lewis structure and predict what the hybridization of an atom is. That's it, and you'll see that. Anyway, it ends up when the electron group geometry about an atom is trigonal planar, it has to be what we call sp2 hybridized in hybridization theory. For example, in ethylene here, in this carbon here, there's 1, 2, 3 electron groups. Remember, a double bond counts as 1 electron group. And 3 electron groups form 120 degree bond angle, trigonal planar geometry. And so we say that we take the 2s from carbon and 2 of the 2p's and mix them together and make 3 equivalent sp2 orbitals, which are 120 degrees from each other and form a trigonal planar geometry. And in terms of the energies of the orbitals, now we're only taking 2 of these 2p orbitals. We're gonna leave one of these guys unhybridized, and so we're gonna mix together this and 2 of these. We get 3 sp2 orbitals, which are between the energies of the 2p and the 2s, and we get an unhybridized 2p orbital. We take these 4 electrons, pop them in there, and I'll show you in a minute how that forms the double bond here on these single bonds. So we have to make a couple definitions here for you. A sigma bond. A sigma bond is when any 2 orbitals from different atoms overlap head-on, kind of like this sp2 on the carbon in ethylene with this sp2 on this carbon in ethylene. They're just bumping heads right here. They overlap. When they do, the 1 electron from here and the 1 electron from here has an area where they can both exist. We satisfy the octet rule, by the way, for each carbon. And we get a sigma bond, head-on overlap. Now, remember that unhybridized p orbital on the carbons in ethylene? We're still on the same molecule here. That p orbital, that unhybridized p orbital, is perpendicular to the trigonal planar geometry. The 3 sp2 orbitals are in a plane, and the p orbital is perpendicular to that. And so in ethylene, we have 1 on each of the 2 carbons. There's the electron in that p orbital. And what happens is this orbital and this orbital overlap sideways, kind of like that. And they form what's called a pi bond. So a pi bond, this is the definition, it's the sideways overlap of 2 unhybridized p orbitals. Now, in a sigma bond, it's head-on overlap, and any kind of orbital can overlap with any other kind of orbital. But a pi bond has to be a p orbital, and it has to overlap sideways. Pi bonds are weaker than sigma bonds. So a double bond, which you'll see in a minute, is a sigma and a pi. It's not quite double the strength of a single bond. But this is how that double bond forms in ethylene. The sigma bond is one part of the double bond. That's an sp2 on this carbon with an sp2 on this carbon. And the pi bond is the second part. That's a 2p on this carbon with a 2p on this carbon. And this overlap, it's on the top and the bottom. This is all one region of overlap. Then we get a pi bond. So this is important right here. Every time you have a single bond, it's a sigma bond. And as far as we're going to see, every double bond, it always consists, and this is what you should remember, a double bond is always a sigma bond and a pi bond. One sigma, one pi is a double. A triple bond is a sigma, one sigma, and two pi bonds. And because the p orbitals are 90 degrees to each other, the two pi bonds also have to be 90 degrees to each other. Like in nitrogen, N2. So there are two electron groups on each nitrogen. 1, 2. Remember, the triple bond counts as one electron group. And two electron groups gives you linear geometry, electron group geometry, which tells you right there that it's sp hybridized. And so what we do is we take an s and one of the p's from each nitrogen, mix them together, make two sp hybrid orbitals, and we leave two of the 2p orbitals unhybridized. And so we get, notice these two electrons here, that's that lone pair right there. This unpaired electron here is going to go into making the sigma bond of the triple bond here. It's going to overlap with the same electrons on the other nitrogen atom. This is one nitrogen, there's the other nitrogens just like this. So we get an sp on this nitrogen, that has one electron in it, overlapping with an sp orbital on this nitrogen, which also has one electron in it, to form a sigma bond. Right there, just like this. Now we have these two unhybridized 2p orbitals on each nitrogen, each has one electron in it. They also overlap in a sideways manner, and they're perpendicular. There's one p orbital, they'll overlap here. The other ones are perpendicular, 90 degrees, they overlap there. And then we get a triple bond, a sigma and two pi's. Carbon dioxide, it ends up is also, the carbon is sp hybridized. And you can tell that by looking at the Lewis structure, because the carbon atom has two electron groups on it. Two electron groups is sp hybridized. Now, the oxygen's out here. How many electron groups does each of those have? Right, 3, right? 1, 2, 3. And 3 electron groups, remember, is sp2 hybridized. And so we can say in carbon dioxide that carbon dioxide has two sp hybrid orbitals, one going this way and one going this way, and two unhybridized 2p orbitals. They'll be perpendicular and coming out in the plane there. The oxygens are sp2. They have 3 sp2 hybrid orbitals. 2 of those will have lone pairs in them out here. One of those will make the single bond, overlapping with making a sigma bond by a head-on overlap with an sp on the carbon, just like this. And the oxygens, sp2, each has one unhybridized p orbital. One's going to overlap with this p orbital on the carbon, make a pi bond there. The other's going to be 90 degrees to it. See how it twists around here? It overlaps in the plane. We get the double bond on each side. So the upshot of all this, what you need to take away from this really, is you need to be able to predict the hybridization of an atom in a molecule by looking at its Lewis structure. So first you're going to draw its Lewis structure. That's an important step. And then you just count how many electron groups, or effective pairs they call them here, on that atom. If there's 2, it's sp, 3, it's sp2, 4 is sp3, 5 is what we call dsp3, or also sp3d. I'm used to saying it like this, sp3d. Either way is okay. And 6 would be d2sp3, or as I'm used to saying it, sp3d2. So make sure you memorize this, and you got it.